Hi, my name is Beth Bell, and I am an assistant project scientist at UCLA. Today I'm going to be talking about the earliest evidence for life on Earth. And I want to start off by pointing out two very inconvenient facts for people who are trying to interrogate the early geologic record to look for evidence of early life. And the first is that we do not have a continuous geologic record, but moreover, we do not have a continuous geologic record to the formation of the planet around 4.5 billion years ago. In fact, the oldest yet identified rock, which is agreed upon by the community, is a little over 4 billion years old. And although we have a mineral called zircon, which is very convenient and can be dated very precisely, this goes back to nearly 4.4 billion years ago. This can give us some information about what the crust looked like, but it leaves us with relatively scant direct evidence for the surface environment in which we can imagine most life would have existed. A second very inconvenient fact is that we have a somewhat tenuous grasp on the timing and mechanisms by which the very earliest Earth, which during planetary accretion must have looked much more like this than like the nice blue planet we know today, how that transitioned to much more clement conditions. Now we have evidence from the geochemistry of these zircons for liquid water on the surface of the planet from about 4.3 billion years ago at least. However, the earlier period of Earth history and exactly how we went from this somewhat nasty early period to a habitable Earth is still somewhat up in the air. And for the portion of early Earth history that does have a geologic record, there are additional challenges. First, we must ask how early it is appropriate to apply uniformitarianism as an assumption for interpreting the geologic record. And this can be summed up in the phrase, the present is the key to the past, the idea that the processes that are currently shaping the surface of the Earth and its crust are applicable in the past. So let's say we want to look at a sandstone that was deposited 3 billion years ago and understand the structures we find in it. We could look at places where sand is being deposited on Earth today and get an idea about that. Now we do know many ways in which the early Earth was similar to or different than the modern world. We can see early evidence for liquid water, as I had mentioned. However, we do know that atmospheric oxygen, that's a big thing, that was not present prior to 2.5 billion years ago. And so this is going to obviously have a big effect on the biology that could exist, as well as on any prebiotic chemistry that existed and the geochemistry of the interface between the crust and the atmosphere, as well as ocean chemistry. So this is a big thing to keep in mind here, the oxygen history of the atmosphere. We also know that the moon would have been much closer to Earth during the Hadean and Archean, and the day consequently would have been shorter, but the exact history of the moon's migration is not entirely clear. It is also not entirely clear when plate tectonics started. This is the mode by which the Earth currently loses its heat and the lateral movement of plates against each other. And also the exact amount of continental crust that would have existed at any given time in Earth history. And the reason I am singling out the continental crust, in contrast to the crust that underlies the ocean basins, is because the continental crust is far more chemically evolved and concentrates many of the inorganic nutrients that are necessary for biology today, as well as most likely prebiotic chemistry, phosphate in particular. And so I'm showing you here a nice compilation of different models for the growth history of the continental crust put together by Jun Korinaga. This goes from the present day back to the formation of the planet 4.5 billion years ago, and on the y-axis we have the fraction of modern day continental crust. And this just shows you the wide range of models. So sort of a minimum estimate comes from just tabulating the ages of rocks that are currently exposed on the Earth's surface. And you can again see another major problem with the early geologic record is that we have this big dwindling in the amount of rock at any given age. And so this is also going to present challenges for trying to interpret the early record of life. And these models run the gamut all the way to models that have us actually currently losing continental crust, having reached a high sometime in the distant past. And so this is one of the big open questions, is how much of that a very evolved crustal material that could be giving us these inorganic nutrients existed at any given time. And another A major challenge in the early geologic record is that virtually all preserved Archean rocks, by which I mean rocks older than 2.5 billion years, have been metamorphosed to some extent. Now, metamorphism occurs when a rock is subjected to heat and pressure, either through burial from younger rocks or squeezing and straining during tectonic events. And this causes the rock to undergo chemical and textural changes, which can obscure and in many cases destroy evidence for biology that previously existed in the rock. So how do we deal with this very challenging early geological record in the context of the origin of life? We will first turn to what needs to be established in any given case to decide whether a microfossil is indeed biogenic or is abiogenic. We will then apply this knowledge to a series of case studies between 3.4 and 4.1 billion years old, and we will briefly wrap up with future directions in origins of life research. So I want to start out in framing our discussion on three main questions. First and foremost in our minds at this meeting is the structure we are looking at biogenic or abiogenic? Could abiogenic processes possibly create a structure mimicking what we think is biology in this case? And if so, what is the likelihood of biogenic versus non-biogenic origins? Second, and potentially not as widely appreciated outside of geology, but how old is the rock or mineral containing our biosignature or biological structure, and how well can it actually be dated? Third, if we can establish that this signal is biogenic and it is in a very ancient rock, is it actually primary and native to the rock in which it is found, or could it potentially be ascribed to later alteration? When we are trying to establish biogenicity, multiple lines of evidence is really going to be ideal if we can say morphologically these resemble cells, and then we can go in and see that they are associated with organic carbon, and moreover that organic carbon has an isotopic signature that is consistent with a biologic origins, then we can make a very strong case that we are looking at evidence for life. So the starting case is often going to be morphology. These look like cells, and these are some examples from Bill Schaff and his group of different morphologies of microfossils that have been found in Precambrian metasediments. And you can also go in and get very nice 3D reconstructions of these. I'll look for evidence of organic carbon. We'll get more into how you do this, not only on the microscopic scale, but also on the scale of an outcrop or of several centimeters. You can find these larger structures built up by microbes. For example, stromatolites. Here's an example of living stromatolites from Shark Bay, Western Australia. These do still exist in a few places on Earth today, and they are found quite often in the Precambrian sedimentary record. So these are microbial mats. The living mat is on the surface, and they have trapped sediments which have built up these mounds. So here are some cross sections through these mounds. You have these very fine laminations here as the mat was built up. And here is a plan view on top of the outcrop here and here, also showing these nice conical structures that tend to form. Now, let's say you've identified structures that you suspect to be microfossils and you want to check that they are indeed biogenic. A good first step would be to identify organic carbon in association with them, for which you might use Raman microscopy. So you are going to take your sample and shine a laser through it using a confocal microscope, which gives you excellent depth resolution on the order of about a half a micron. And the laser that you shine through is going to interact with various bonds in the different compounds in your sample. It's going to be scattered back and with these characteristic shifts associated with different bonds. So your polymer that you mount your materials with might have these characteristic CH stretching shifts, and graphite in your samples will have these characteristic G band and D band, as we call them. The G band is associated with nice crystalline, highly ordered graphite. The D band is associated with disorder in the graphite spectrum. One really nice thing is that the relative strengths of the G band and D band have been calibrated as a thermometer for the temperature at which graphite equilibrated in its host rock, and the G band and D band are also present in other forms of organic carbon, such as kerogen, which is partially matured hydrocarbons found in many examples of microfossils and throughout the geological record. So here's some examples of different levels of maturity of these different carbonaceous materials. Diamond also looks quite distinct here. And here's an example of what you can do with the Raman microscopy. On the left, you have visible light images of these materials, which are suggested to be microfossils. And on the right, these are maps of the graphite G band, showing that this organic carbon material is actually quite closely associated with these proposed microfossils, which makes a very good case for these, in fact, being biogenic. Now, an associated technique, which has been used quite extensively by Bill Schaaf and his group, is confocal laser scanning microscopy, which uses a laser to excite fluorescence in kerogens, which allows for very nice 3D reconstructions of the geometry of these microfossils. And a final very strong piece of evidence for biogenicity comes from the carbon isotopic composition. Now, we are going to be using the quantity delta C13, so for those who are not familiar with it, we are talking about the ratio of the stable carbon isotopes 13 to 12 relative to a standard. We usually use PD belemnite, and what we are seeing on this graph here, we're dimensionless on the x-axis, and on the y-axis we have delta C13. So in parts per thousand or per mil, you can see that inorganic carbon, which will be, say, carbonate rocks, limestones, also things that are outgassed from volcanoes, for instance, tend to be relatively isotopically heavy compared to biogenic carbon. And this is because enzymatic carbon fixation tends to favor carbon-12. And there are a variety of different metabolisms that affect different levels of fractionation. They can even become more extreme than what is shown here. However, over geological time, again, we're seeing delta C13 versus age here. There tends to be a relatively steady average of around a -25 per mil offset of organic carbon, shown here by kerogens, from inorganic carbon, shown here by carbonates. This is a nice compilation put together by Bill Schaaf, showing that although there have been some excursions here and there, this -25 per mil offset has been studied back as far as around 3.5 billion years ago. Now, there are some caveats here with using light carbon as a biosignature, because there are potential sources of abiogenic carbon, and that it has this light isotopic signature. We should go over some of them now. So probably the most likely origin of abiotic carbon in the early Earth is carbonaceous chondrites. Now, this is a class of meteorites which is very rich in carbon. And the various carbonaceous compounds in these meteorites have a wide range in carbon isotopic compositions. However, the average of the bulk carbon in this meteorite class is -12 per mil, so shifted somewhat heavy compared to kerogens on this scale, but overlapping. Now, there are various terrestrial sources of light abiotic carbon, such as degassing of magmas at mid-ocean ridges. We cannot rule out some level of abiotic, say, Fischer-Tropsch synthesis in the deep earth, as the source of some light biogenic or abiotic carbon, rather. Carbonate mineral breakdown has been suggested as a source of a light graphite. A study by Van Zwijlen and others showed that the decomposition of siderite, which is an iron carbonate mineral, to graphite could lead to a -6 per mil shift. So this is a relatively small shift compared to the average for carbonates. You could also imagine diffusive fractionation of carbon through native metals, which has been shown to fractionate carbon-12 from carbon-13. Now, native metals are relatively rare in Earth's crust and tend to be formed only in the sort of ore systems, hydrothermal systems around cooling magma bodies. So this would be a very spatially specific source of abiotic light carbon. Now, how are we going to make these carbon isotopic measurements? Well, if we want to be able to look at individual microfossils or individual components of our rock and find potential heterogeneities in the carbon isotopic composition, we are going to want to use secondary ion mass spectrometry. And this is in contrast to, say, crushing up the bulk rock and taking a measurement that averages all of that material. So how a secondary ion mass spectrometer or ion probe works is that we have what we call a primary ion beam. In the case of a carbon isotopic analysis, this will be a cesium ion beam. We have a solid sample. We simply take our rock and polish it down flat. We hit it with our ion beam. We can do this on the order of several microns in diameter with the spot that we hit our sample. This liberates some material, some of which is ionized. This is then drawn into our mass spectrometer for an isotopic ratio analysis. And one of the great things about SIMS as a technique is its high spatial resolution. So this is an example from Chris House, where on the left we have optical images of these microfossils. On the right we have ion images of the same microfossils in carbon-12, and you can see the very close association of carbon with the walls of these cells. And they were also able in this study to go in and put spots on these individual microfossils, spots just a few microns in diameter, and able to get precise delta C13 on these individual microfossils and relate different carbon isotopic ratios to different types of microfossils here. So both ion imaging and these spot analyses for isotopic and composition is something that SIMS routinely does. Now, different tunings of the instrument will also allow us to uranium-lead date our rocks and be able to more clearly establish the age. So this is a very adaptable technique with a wide range of applications in the early Earth. So here is a table summing up the lines of evidence that would be used to establish biogenicity in cases of microfossils, stromatolites, and graphite that is distributed throughout a rock and not particularly associated with obvious stromatolites or microfossils. We would want to be able to find a delta C13, morphology suggesting stromatolites or cells, find evidence for organic carbon. All three of these together would make the strongest case for biogenicity. However, the older the candidate case, typically the fewer lines of evidence are going to be available to us, and often the greater metamorphism the rock has seen, which is going to erase some of these lines of evidence. We will also, in many of these cases, need to deal with various caveats about ways that abiotic features could mimic these potentially biological features. Now we need to determine the age of our rock or mineral of interest. And if we are looking at a rock that was cooled from a magma, then we are often going to be able to use a radiometric technique to directly date it, such as zircon, which is a mineral that tends to concentrate uranium as it grows from the magma and exclude lead, which allows us to very precisely uranium-lead date them, and therefore the magmas in which they grew. And there are various other radioisotopic techniques. One in particular uses an extinct nuclide called samarium-146, which in very ancient materials, excesses of neodymium-142 can be used to infer the original presence of samarium-146 and get some additional constraints on age. Now, when we are looking at fossils and stromatolites, we are going to be looking at the sedimentary record. And so most sedimentary rocks are not going to be conducive to absolute dating by these radiometric techniques. And this is because the sediments will either be clastic, which means that they are bits and pieces of older rocks which have been cemented together and might have any number of an array of ages, or they are going to be chemical precipitates, which for the most part are going to consist of minerals that are not conducive to these direct dating techniques. So we're going to have to use a variety of relative dating techniques. So for example, we have a packet of sediments that are being deposited in a basin. We know that the oldest, which are deposited first, are on the bottom. The youngest are going to be on the top. And then sometimes we will be lucky enough to have a cross-cutting igneous dike come through, which we know is younger still. And sometimes we will also be lucky enough to have interbedded lava flows or ash falls, which can also be directly dated using radiometric techniques, which can allow us to further nail down the ages of the sediments in which we are finding our fossils. Now, on a smaller scale, these relative dating techniques can be used to determine whether or not a particular signal is original to the rock or mineral in which it is found or could be due to later alteration. So I'm going to use an example of my own work. What we have here is a zircon, which it's been mounted in epoxy. That's what this background material here is. Now, the materials that we see in this particular image here are first a grain of zircon. There is an inclusion of quartz within the zircon. It is fully enclosed. It is not associated with any cracks. And then lastly, we can see that there is this crack which goes through the zircon and has been filled by this later phosphate phase called xenotime. Xenotime also fills this void space that was adjacent to the crack. Now, the sequence of events we can see here. First, we have this quartz. This is the oldest material that we see in this image. It was then included in this zircon, which grew around it. And then after this zircon had formed, it cracked open and metamorphic fluids came in and deposited this xenotime. Now, if we were to be looking in this inclusion, which is adjacent to the crack here, and we found some biogenic carbon there, or we would not be able to say that it is definitely as old or older than the zircon in which it is found, because it could very easily have come in with metamorphic fluids that we know invaded this crack. However, if we were to find biogenic carbon away from cracks, say associated with this quartz or elsewhere in this zircon, then we would know that it is the same age or older than the zircon that encloses it, based on these textural relationships. And we do the same thing on the scale of a rock. What are the oldest minerals that we find in this rock? What is the oldest mineral fabric that has been developed? Has it been overprinted by later metamorphic minerals? And we can make determinations about what is primary and what is secondary in the rock based on these techniques. So we will now move on to looking at a series of case studies, and we want to keep in mind our three main questions. Is the signal we're looking at biogenic? How old is the rock it is found in? And is this rock primary to the rock that we find it in? Now, there are a number of proposed biogenic cases between 3.4 and 3.5 billion years in age, and I'm pulling out one in particular that is a quite good example, the Strelley Pole Formation in the Pilbara Craton of Western Australia, because it contains both interpreted microfossils as well as stromatolites. Now, it is worth mentioning that the stromatolite features in this rock had been noticed in the literature for quite some time, and there's quite a bit of controversy over whether they are biogenic or abiogenic. However, more recent close textural and chemical examinations of these stromatolites, finding organic carbon associated with these laminations and that it is light isotopically, have helped to establish the biogenicity, and the microfossils in particular are associated with kerogens that are isotopically distinct from the carbon in the surrounding rock, and so this is now a relatively well accepted case in the community for biogenic origins of these microfossil features. We will now turn to the apex chert, which is also found in the Pilbara Craton of Western Australia, where microbial filament-like structures are associated with organic carbon that has light delta C13, and these have been interpreted as fossils of microorganisms associated with ancient hydrothermal systems. So on the left, we have these visible light images. On the right, this Raman mapping showing graphite closely associated with these microfossils. Now, this is somewhat of a controversial result, and there has been a long argument in the literature about the biogenicity of these fossils. Here are some studies you can check out here arguing for abiotic origins. Now, another example of similar age, also from Western Australia, is stromatolite-like structures in the Dresser Formation. The high degree of weathering had for a long time stymied more certain identification of biogenicity. However, more recent studies of more pristine materials recovered from drill cores here have allowed a closer study of these materials. So you can see these stromatolite-like structures in here. They've been mineralized by pyrite here, a sulfide mineral, and mineralization with pyrite is also something that we see with organic carbon more recently in the geologic record. And so these more pristine materials have allowed closer studies with both SIMS, here's some isotopic mapping, as well as Raman, to identify organic carbon in here associated with these pyrite structures, and a more clear case for the biogenicity of these stromatolites. So we have now stepped 200 million years further back in the geological record, and we are at Ishua in southern West Greenland, looking at marine metasediments which have been relatively highly metamorphosed. So most of these metasediments have seen a fairly high level of strain, which have changed much of the original rock fabric. However, the authors of the study identified a relatively low strain zone in these metasediments, including features that they interpret to be stromatolites. To preserve original sedimentary bedding, you can see these fine laminations here, and these features which they interpret as stromatolites. They look conical on this particular outcrop here, and they contain carbonate minerals that have chemistry somewhat like seawater. And so the authors interpret this as stromatolites that are fortuitously preserved in this low strain zone here. And the 3.7 billion year age, which is established by cross-cutting relationships with igneous dikes elsewhere, makes these the oldest proposed stromatolites yet on Earth. However, this is a relatively controversial study, and a number of follow-up studies have suggested abiotic origins for these features. In particular, two studies that have looked at slices of this outcrop perpendicular to what we are seeing here, and have concluded that these are not in fact conical structures as would be suspected for stromatolites, but are in fact ridges and could more appropriately be assigned to tectonic strain as their origins. Now that there is some controversy ongoing here, and the authors of the original study have also pointed to potentially biogenic ridge-like structures as an origin, but there is a lot of ambiguity in the origins of these particular structures here. We now turn to the new Wagonic region on the eastern shore of Hudson Bay in Canada, and this is a belt of ancient Archean rocks largely made up of metamorphosed basalts with some associated metamorphosed sandstones and silica units, many of which have been interpreted as potentially ancient hydrothermal systems. And in these silica units are hosted these structures that have been interpreted as microfossils. Now, the age of this belt is somewhat in question here, and this is largely to do with the extinct samarium-146 neodymium-142 isotopic system that I had mentioned earlier in this talk. There are anomalies in neodymium-142 in these metamorphosed basalts, which are consistent with either an age of around 4.3 billion years. For this interpretation, you can look up studies by Jonathan O'Neill, or with the contamination of much younger lavas by materials 4.3 billion years in age. And for this latter interpretation, you can look up studies by Nicole Cates. In particular, the youngest zircons in sandstones that are associated with these basalts is 3.78 billion years in age, which suggests potentially much younger origins for much of the materials in here. And the belt is overall cross-cut by granitic dikes that are 3.75 billion years in age. So these proposed microfossils are found in the silica units, and they consist of tubular structures made up of nanocrystalline iron oxides. There is organic carbon in the silica unit, although it is not directly associated with these tubular structures, but is in other structures found adjacent to them in this silica unit. So there is a controversy associated with these results, in particular the idea that these tubular structures could potentially be formed abiotically in nature, as a later study has suggested, as well as questions about the potential origins of abiotic light carbon. We will now move back to southern West Greenland in marine metasediments, which are cross-cut by a granitic dike that is 3.83 billion years in age. And these metasediments contain a calcium phosphate mineral called apatite, in which are inclusions of graphite with a light delta C13. And you can see that these have a wide range in delta C13, but they are overall consistent with biogenic origins, having that very light isotopic ratio. Now, a number of controversies have arisen about this study in the years since it has been published. I had mentioned potential sources of abiogenic light carbon earlier in the talk, and in fact the idea of carbonate decomposition being leading to these light carbon isotopic ratios was proposed for this particular case. However, the relatively small shifts that you can get from the decomposition of carbonates to graphite in this case is not going to yield these very light isotopic signatures in many of the graphites that were found in this study. Now, some studies had questioned where exactly the graphite is found in this rock. Is it actually enclosed in these apatites? Is it a later film, or is it there at all? However, a very nice follow-up study by Kevin McKeegan and others was able to locate inclusions of graphite in apatite exactly as reported by Steve Moisich in his original study, and was able to isotopically characterize these via SIMS and find that they are isotopically light as found in Steve Moisage's original study. Now, unfortunately, the apatites here cannot be directly uranium-lead dated to get an age for the graphite because apatite tends to lose lead relatively readily during later metamorphism. So the apatites are 1.5 billion years in age, yet the best constraints we have for the actual age of these sediments remains this 3.83 billion year age from the cross-cutting relationship. We will now move to the Saglec block in Labrador, Canada, which contains metasediments that have been interpreted on the basis of cross-cutting relationships to be 3.95 billion years old, and they contain isotopically light graphite, which have been interpreted as original to the metasediments based on various textural relationships. And these have been proposed by the study authors as evidence for biogenic carbon as early as 3.95 billion years ago. Now, there are a number of controversies here. There's always questions raised about abiotic sources of light carbon, but in particular, the cross-cutting relationships used to establish the age of these metasediments have been brought under question in recent studies, suggesting that they are not really applicable to the outcrops in which the carbon here is found. Now, our final case study is one of my own. What we are looking at here is a 4.1 billion year old zircon originally grown in a magma, and it contains two inclusions of graphite, which are isotopically light, shown here, and it is consistent with what we see for kerogens throughout geologic history. So we interpret this as a biogenic carbon assimilated into a magma, which was trapped by our zircon. Now, this is a controversial result. In addition to the usual questions about abiotic sources of light carbon, a number of people have suggested that this carbon is in fact secondary. Now, we went to some pains to show the primary nature of this carbon, and in particular, we showed with transmission X-ray tomography at a 40 nanometer spatial resolution that there are no cracks associated with these graphite inclusions that could have allowed the migration of the carbon in over geologic time. The relatively disordered nature of the Raman spectrum of the graphite has been pointed out as inconsistent with the high temperatures associated with magmatic formation. However, one thing we do note is that this graphite has been included in this zircon for 4.1 billion years, and the zircon has 100 parts per million of uranium. And so this graphite would have accrued a fair amount of radiation damage over geologic time. Now, whether this can account for the level of disorder seen in the graphite crystal structure is not something that we have been able to test so far. It is something that we are looking forward to testing when we have further examples of graphite inclusions in other Hadean and Archean zircons. So now let's summarize what we've seen from carbon isotopes as well as stromatolites and microfossils in the early geologic record in the context of when we have a secure agreed upon rock record and the time over which we have zircons. So there are a number of cases between 3.4 and 3.5 billion years in age for which there are multiple lines of evidence that can be marshaled, which give a fairly secure case for biogenicity that is relatively well agreed upon. And things that are 3.5 billion years and older also tend to accrue various levels of controversy. Now, in particular, when we are going to take these carbon isotope ratios out of the context of clear morphological evidence for stromatolites or microfossils, it becomes a little bit less certain whether or not we can rule out abiotic sources of carbon. In particular, even though we know that the graphite included in the zircon here is 4.1 billion years old or older, that zircon has been divorced from its original context, has been eroded out of the granite from which it originally grew, and it becomes that much more difficult to link it to whatever biology may potentially have created that very clearly fractionated carbon isotopic ratio. So as we get further back in geological history, it is much more difficult to marshal these multiple lines of evidence for any given case. We have challenges also from the paucity of older rocks, that dwindling of the rock record with time. Although we do have zircons that get back to nearly 4.4 billion years in age, again, we run into those problems with the fact that they have been taken out of their original context. Now, that being said, I will fully admit to being a zircon partisan and think that zircon is really one of our best routes for pushing back early carbon isotopic evidence earlier into geological history, as well as potentially evidence on the origin of life. Now, only at the Jack Hills location in Western Australia, we have zircons nearly back to 4.4 billion years in age, and we are continuing to search these for more instances of graphite that can be isotopically characterized. But there are now 15 known locations on Earth in which zircons older than 4 billion years have been found, and each of these is a potential scientific gold mine for looking at first conditions in the early crust, what materials made them up, and also can we find other instances of early carbon or other materials that might be able to tell us about early life? One other example would be potentially sulfide inclusions, which, if they can be isotopically characterized, might also be able to yield information about early life and metabolisms. Now, in addition to sites with Hadean zircons, there are sites with early Archean metasediments. Metasediments might be searched for in any number of locations, and potentially we might get lucky and find areas that have not been as highly metamorphosed as most rocks of that age have been, in which we can marshal multiple lines of evidence for biogenicity and potentially push the microfossil record back even further. I want to leave you with some recommended reading, some review papers that I found very helpful in putting together this talk, and I thank you for listening.